Hello, and welcome back to Let's Data Science. Today, we are diving into Google's Gemma 3 models hands-on. If you caught my previous article about Gemma 3's impressive features, like its 128,000 context window and multilingual capabilities, today we are taking things further by showing you actual performance metrics from running and testing these models on real hardware. I have thoroughly tested all four variants, from the lightweight 1 billion parameter model all the way up to the powerful 27 billion version, comparing how they stack up against each other on a range of practical tasks from basic Q&A to complex code generation, summarization, and multilingual capabilities. For these comprehensive tests, I used GCP Workstation equipped with two NVIDIA A140GB GPUs. This high performance setup gives us the necessary horsepower to handle even the largest 27 billion model. Though, as you will see in the results, the memory requirement varied dramatically between the versions. Let's start by walking through the environment process. First, we create a dedicated virtual environment. Next, we install the necessary packages. We need several key libraries to work with these models. Importantly, Gemma 3 requires a specific version of Transformers library due to its architecture, so we need to install that custom branch. Since Gemma 3 is a gated model on Hugging Face, we need to set up our access token in a .env file. This is a simple text file that looks like this. Now, before running the models, there is an important distinction to understand. For each parameter size, Gemma 3 offers two variants, the pre-trained base model and the instruction-tuned models. The base models are primarily designed for further fine-tuning, while the instruction-tuned versions are ready for direct use in applications. For our practical testing, I use the instruction-tuned variants since they are optimized to follow natural language instructions and produce more useful outputs. Now let's talk about running these models. I needed to use two different test scripts because the architectural differences between these two model sizes. For the 1 billion model, which is text only, I ran it using the following command. For the 4 billion, 12 billion, and 27 billion model, which all supports multimodal inputs, I used the following commands. During testing, I monitored GPU usage with the NVIDIA SMI command. This is a crucial command to know when working with large language models, as it helps you understand your resource utilization in real time. The memory jumps dramatically as each model loads, from under 2 gigabits for the 1 billion model to over 52 gigabits for the 27 billion model. My testing evaluated each model across four comprehensive categories. Basic Q&A for testing general knowledge and reasoning abilities, code generation to assess the programming capabilities across multiple languages, summarization to evaluate text comprehension and condensation skills, multilingual support across Spanish, French, Chinese, Arabic, and German. For each task and model size, I carefully measured three critical metrics. What is the load time, like how long it takes to initialize the model in memory? What is the inference time, response generation speed across different types of queries, and the memory usage, the detailed VRAM requirement throughout the process. Here are some of the most interesting findings from my testing. The 1 billion model is surprisingly capable for its modest size, loading in under 6 seconds and using less than 2 gigabits of VRAM. It handles simple Q&A and basic code generation quite well. Though it sometimes produces unnecessarily verbose responses, it's perfect for resource-constrained environments or edge devices. The 4 billion model introduces multimodal capabilities with only a moderate increase in resource usage, around 8 gigabits of VRAM. In my testing, it delivers notably more coherent and concise answer than 1 billion model, particularly for complex reasoning tasks and code generation, with inference time averaging around 30 to 45 seconds for complex queries. The 12 billion model represents what I found to be the sweet spot for many applications, with significantly improved response quality and depth while still fitting comfortably on a single A140GB GPU. It requires about 23 gigabits of VRAM, but delivers substantially better performance on nuanced questions and complex code generation tasks. The 27 billion version shows the most impressive performance quality-wise across all test categories, with particular strength in multilingual capabilities and reasoning, but requires over 52 gigabits of VRAM to load, pushing the limits of even our dual A100 setup. This model is best suited for professional deployment where quality is paramount. With a complete performance breakdown, including detailed charts, comparing load times, inference speeds across different task types, memory scaling with model size, and actual output samples from each model, be sure to check out the full article on Let's Data Science blog. Thank you for watching. If you found this practical breakdown helpful, please consider subscribing and checking out the detailed results in the full article. Until next time, stay curious and let's data science.